the distance of lambda by 6, both radiation and induction terms has equal magnitude. That is, both 1 by r cube and 1 by r square terms has same magnitude at a distance of lambda by 6, which we can derive also. For derivation you can refer any standard textbook. Suppose this is the antenna. The next point is, this is the antenna what we are considering. Dipole antenna. The radiation pattern, this is the basic antenna we are considering. Dipole. The radiation pattern looks like this. The radiation pattern looks like this for a dipole antenna. Similarly, this side also. Like this. It's continuous. The propagation continues. So the radiation pattern is like this. For the dipole antenna, what we are considering. And suppose if the current carried by Cartesian dipole is I is equal to I naught cos omega t. Suppose I is equal to I naught cos omega t. Then power radiated by the antenna, or power radiated is given by power radiated is equal to half into I naught square into R radiated, which is very, very important. So here all the points, whatever point we are mentioning in this particular antenna concept is important, because we are discussing only the conclusion points. So the power radiated is equal to half into I naught square R radiated. So what is this R radiated? We will see. So this where R radiated is a characteristic property. It's a characteristic property of the Cartesian dipole antenna. Cartesian dipole antenna, and is called radiation resistance. Radiation resistance of the antenna, or it's called radiation resistance of Cartesian dipole, which is very, very important characteristic of the antenna. So this is already we discussed transmission lines. So transmission lines are characterized by its characteristic impedance. Similarly, the antenna is characterized by radiation resistance. This is one of the characteristic of the antenna, and this radiation resistance is given by 80 pi square into dl by lambda whole square, where dl is the length of the Cartesian dipole by lambda. Of course, even though this is a formula for radiation of a Cartesian dipole, this formula valids for any antenna of any length. So this formula is very, very important. You have to keep in mind this formula. The radiation resistance is equal to 80 pi square dl by lambda whole square. We know that lambda is cutoff wavelength C by f. We can calculate by using C by f, where dl is the length of Cartesian dipole. Suppose, for example, if dl is equal to lambda by 10, then what is approximately radiation resistance is 80 pi square into lambda by 10 whole square. Lambda by 10 by lambda cancels, 1 by 100, 1 by 10 whole square, 1 by 100. So this is approximately equal to how much? So pi square is approximately 10. So pi square approximately we can take as 10 means, so this is approximately 8 ohms. Approximately 8 ohms. Therefore, radiation resistance, if you observe this equation, the radiation resistance depends upon length of the antenna as well as lambda, where lambda is C by F, that is frequency of operation. Therefore, radiation resistance of Cartesian dipole antenna depends on wavelength and length of the antenna. And the next property is radiation efficiency. Radiation efficiency of antenna. It is given by eta R, radiation efficiency. The definition is eta R is equal to power radiated by power input. So it is given by eta R is equal to R radiated by R radiated plus R loss. This is the formula for radiation efficiency of a antenna, where R loss is loss resistance of the antenna, because we will have some losses. So R loss is a loss resistance of the antenna. Loss resistance of antenna. So directly we can calculate by using this radiation resistance. Suppose if you know radiation resistance and losses, suppose if loss is 0, then what is the efficiency? 100% efficiency. So loss is 0 means it is a 100% efficiency. That is power radiated is equal to power input. The next one is half wave dipole antenna. So this is a particular antenna. We discussed Cartesian dipole, which is length is very small. Half wave dipole, in the name itself, the length is lambda by 2. The length of the antenna is lambda by 2. Half wave dipole antenna. So in Cartesian dipole, what is the problem? In Cartesian dipole, we assumed the length is very small. The length of the antenna is very small. So we know that radiation resistance is equal to 80 pi square into dl by lambda. So it directly proportional to length. So which implies its radiation resistance is very small. Its radiation resistance is very small, which is very clear for us. Radiation resistance is very small. So radiation resistance very small. Actually, generally, what is the basic procedure? This is the transmission line. We have to match this transmission line to a antenna. We have to match this transmission line to a antenna. This is transmission line. This is antenna. So we have to match the transmission line to a antenna. Generally, transmission lines are 50 ohm, 100 ohm transmission lines exist. Since this radiation resistance is very small, in practice or in practical or in reality, it is difficult. It is difficult to match it with a real transmission line. Cartesian dipole. So therefore, a more practical antenna is needed. A more practical antenna is needed for better matching. Which is half wave dipole antenna. That's why we are going for half wave dipole antenna, because Cartesian dipole radiation resistance is very small. So practically it is not possible to match with a real transmission line. So half wave dipole antenna length is equal to lambda by 2. So a dipole antenna, consider a dipole antenna with a particular length. Suppose this is I. The current distribution is like this. The length is L is equal to lambda by 2. Suppose it is carrying a current I is equal to I naught cos omega t. The power radiated, if you derive, is given by half into I naught square into 73. So I am not deriving here the derivation. So what is the derivation part we used for Cartesian dipole? Same procedure you have to calculate. You have to calculate from starting from E values and H values, then power P is equal to half into real of H cross. Then you will get power radiated is half into I naught square 73. So here it is very interesting. This is 73. If you compare this with Cartesian dipole, where we are getting half into I naught square R radiation, instead of R radiation here we are getting 73. Therefore we can say that R radiation, that is radiation resistance of a half wave dipole is 73 ohms, that is constant, which is very important statement. So the radiation resistance of a half wave dipole is 73 ohms. So remember here, don't put L is equal to lambda by 2 in that 80 pi square dl by lambda whole square formula. Even though the formula is valid for any antenna of any length, this is a half wave dipole antenna is a particular type of antenna designed particularly for some practical reasons. Okay, generally DL is like lambda by 10, lambda by 20, lambda by 50. That is very low when comparing with lambda. So it is not in the range of lambda. Then use that radiation formula. Suppose if lambda is suppose here lambda by 2, 0.5. So if you compare with lambda, this is approximately equal to lambda. So don't use that formula for half wave dipole antenna. Here therefore radiation resistance is 73 ohm. But more practically, if you consider more practical case, the input impedance of a antenna, the input impedance of dipole antenna, Zin. The input impedance for a half wave dipole antenna is given by 73 plus J 42.5 ohms. Where this is radiation resistance, this is reactive part. Some reactive part also we will get. This is the input impedance of a half wave dipole antenna. of your dipole, for a of your dipole, the input impedance. So keep in this mind, it may be helpful if they ask directly what is the reactive part of your dipole. The next one is quarter wave monopole. Quarter wave monopole. Quarter wave monopole. This is a very interesting one. Suppose this is a dipole, I am considering, suppose this is a lambda by 2, total length lambda by 2, total length is lambda by 2, or L, total is L, length is lambda by 2. Now here I am considering a infinite ground. This is a infinite ground plane. Here monopole. Monopole is considered, monopole means only one pole. Dipole means two poles. This is one pole. This is another pole. Here monopole means only one pole. I have to consider only one. So this is, then what happens, this is a lambda by 4. This is lambda by 4. Nothing but L by 2. L by 2. It will become L by 2. So generally monopole length, instead of considering length, I am considering as height. Height of the monopole. Height of the monopole, because I am comparing here with the standard lambda by 2 dipole. I am considering only single pole. So this one. So height of the monopole is H is equal to L by 2, where L is the length of dipole, that is equal to lambda by 4. That is equal to lambda by 4. So basically it consists of a one half of the half wave dipole antenna. Therefore basically the quarter wave monopole antenna, basically the quarter wave monopole antenna consists of one half of half wave dipole. So half wave dipole means it consists two parts. It consists now only one part, like this, only this part. Therefore radiation resistance is, if you compare, this is exactly half. Monopole is exactly half of dipole. So radiation resistance also 36.5 ohms. Radiation resistance of monopole, quarter wave monopole is 36.5. And input impedance Zin is given by 36.5 ohms plus J21.25. 36.5 plus J21.25, exactly half ohms for a lambda by 4 monopole. Lambda by 4 monopole. So this is quarter wave monopole. Now we will discuss a simple problem based on this concept. The problem is a masked antenna. This is a kind of antenna consisting of 50-meter long vertical conductor, operates over a perfectly conducting ground plane. It is base fed at a frequency of 600 kHz. the radiation resistance of the antenna is the radiation resistance of the antenna is option A 2 pi square by 5, option B pi square by 5, option C 4 pi square by 5, option D 20 pi square. The solution to this problem is, this is very simple. Here length is given 50, length is given 50 meters, 50 meters. Calculate lambda. Calculate lambda. Lambda is equal to C by F. Lambda is equal to C by F. That is equal to 3 into 10 power 8 meters per second by 600 kilohertz. 600 into 10 cube. So this is equal to 1 by 2 into 10 cube. 1 by into 10 cube. So 1 by 2 into 10 cube means 1000 by 2. 1000 by 2. 500 meters. So when comparing with the lambda value, L value is very less. So we can use this formula. R radiation is equal to 80 pi square into dl by lambda whole square. Because when comparing with lambda, length is very small. 50 meters is very, 50 is very less than 500. 50 is very less than 500. So we can use directly this formula. So that is equal to 80 pi square into 50 by 500 whole square. 50 by 500 whole square. 50 by 500, that is 1 by 10 whole square, 1 by 100. So 80 pi square by 100. Because here everything, all options are given in terms of pi squares. So this is equal to 24's 25's. So 4 by 5 pi square, 4 by 5 pi square. So radiation resistance is option C. Option C. In this problem, if you observe, this is a direct problem. Direct problem. The only thing here is calculate lambda value and compare with the length. If length is very less than lambda, directly we can go for this formula. We can go for this formula. This is pi square. So option C is correct answer.